All right, so we're going to talk a little bit about momentum today, do a little bit of an introduction here, and then do a few practice problems with impulse. It should be a nice review from last year. It should be something that is not that tricky here. So, momentum is a quantity that describes the amount of motion that an object has. I always think about it as who will win in a collision. In order to win in a collision, you want to be bigger or more massive, and you want to be faster. That's the key. And that's exactly what momentum gets at. So momentum is simply mass times velocity. That's how we're going to calculate momentum. It's represented with the letter P, all right? And it's just mass in kilograms times velocity. It doesn't have a fancy unit here. Its units are simply kilogram meters per second. All right, so that's momentum, just the basic idea of momentum. There are two reasons why we care about momentum, otherwise it would just be a useless quantity. The first one is impulse. So impulse is actually the change in momentum, all right? Delta P is how I always do it. And the reason why impulse matters is we can relate the impulse, the change in momentum of an object, right, to the average force exerted on that object and the time over which that force is exerted. So this idea of impulse, the change in momentum, allows us to analyze, usually collisions is how we're doing it, but it allows us to analyze situations where the momentum of an object changes and we can link it to the average force, all right, that led to that change. All this momentum stuff really comes from Newton's laws and forces. It's simply a new way of looking at it. Okay, so before we go on to the next slide, I want to think for a second about how we'd actually calculate the impulse. All right, so impulse, like we said, is the change in momentum. And of the quantities that make up momentum, mass and velocity, which one is more likely to change? Okay, there are a few situations where the mass could change, but the one that most likely is going to be changing is the velocity. So our change in momentum is simply going to be our mass times our change in velocity. So that's going to be one way that we're going to calculate momentum. And we'll see in a second another way using force and time. So here we have our two equations for momentum, the change in momentum, I should say, which is the impulse. The first is that change in momentum is the mass of the object times the change in the velocity, and that simply comes from our definition of momentum and thinking about what would change, as we saw in the last slide. The other way we can calculate it is that the change in momentum is the average force, okay, exerted on an object. In this case, that's a net force, multiplied by our change in time. And that's the one that really makes this idea of impulse useful. Because we can link that change in momentum to force, it makes impulse useful. Conceptually, impulse tells us something really, really important about collisions. And we can use impulse in any situation, but collisions is going to be a pretty big application of impulse. So, if we have a given collision, for example, we have this car here going and colliding with two different objects, traveling at the same initial speed here to the right. And in one case, it collides with this barrel of hay. The other case, it collides with a wall. What impulse tells us is that for a longer collision, meaning more time for our collision, the force exerted on the object will decrease. All right, so as our time goes up, our force goes down. For a shorter collision, meaning less time, all right, so the case of colliding with a brick wall here, the time goes down, meaning that the force will increase. All right, and that all comes from this idea that the change in momentum is the average force multiplied by the change in time. So if this time increases, that force decreases to keep the same change in momentum. All right, and vice versa. All right, a lot of safety devices operate based off of this principle, mainly airbags and bumpers. They're both designed to extend the time of the collision. Right? An airbag slows you down over a longer period of time than if you had been slowed down by the dashboard or the windshield or something like that. Okay, bumpers in the front of cars that collapse, just like in this picture here. All right, that is a design feature of newer cars. They are designed to have a crumple zone. They are designed to have an area where they collapse. And the reason is that extends the time of the collision. And although your car might be severely damaged and might need a lot of repairs in that situation, it helps to keep you safe. It helps to protect you by extending the time of the collision and thereby decreasing the force exerted on you. Let's think about a few tips here for solving these problems. This is what I always think about. We always have two ways of finding the change in momentum or the impulse. All right, we have the m delta v, and we have the average force times our change in time. So we want to find our change in momentum one of those ways, depending on what we're given. Do we have a mass and a change in velocity, or do we have a force and a change in time? And pick which one we have and find our change in momentum that way, and then use it in the other equation. As always, we want to be careful with signs, okay? I say that all the time, but it's important all the time, so that's why I keep saying it. So let's give this first one a shot here. Why don't you go ahead and maybe pause the video and try it on your own, and I'll go through the solution then in 1 second. But we have this football player running into a wall and rebounding off the wall. And our collision here lasts 0.6 seconds. We want to calculate the average force exerted on the football player. So we have change in momentum is mass times change in velocity. Change in momentum is average force times change in time. All right. So go ahead and think about what we have, set up your problem, and try and calculate that average force, and then go from there. So I'm going to go ahead and work through the solution here. So we have change in momentum is our mass, which we know is 68 kilograms, times our change in velocity. Now the way we're going to get that is by doing V final minus V initial. This is always what we're going to do whenever we have a change. Any change is final minus initial, and in this case we're talking about a change in velocity, so it's velocity final minus velocity initial. So our change in momentum then is going to be 68 times negative 3 minus 8. And the reason why I am doing that is we have our football player here, and our football player is initially traveling in one direction at 8 meters per second, and the football player rebounds in the opposite direction. Okay, the fact that we're rebounding is key here. So that means that our velocities have opposite signs. So one of them better be negative. So either the 8 is negative or the 3 is negative, and I'm just going to make the 3 negative. But if you had said 3 minus negative 8, that would work as well. So we find that our change in momentum here is going to be negative 748 kilogram meters per second. And we're going to take that and put that in over here into our other impulse equation, our other change in momentum equation. And so we're going to say negative 748 is equal to the average force times my time, which I know is 0.6. So I divide by that to 0.6, and I get that my average force here is 1246.7 newtons. Now, it would be negative, okay, because there was this negative sign here. We're really going to be looking for the magnitude of the force, and that's what the problem actually asks for. So when we're solving for that magnitude, that just means take the absolute value, right? Ignore that sign, which indicates direction. All right, so we have a conceptual question here next. We have two identical bumper cars. They're traveling at the same speed. All right, so they're identical. They have the same mass. They're both traveling at the same speed. And what ends up happening is car A runs into a brick wall here and slows down to a stop. So its final velocity is 0. Car B runs into a giant spring and slows down to a stop. So its final velocity is also 0. And we want to explain why there would be more damage using physics to car A than car B. So the key word here is time. All right, that really is the key. All right, so I would say that car B slows down over a longer period of time. And even though they have the same change in momentum, the fact that car B slows down over a longer period of time means its force will be smaller. All right, And we can look at our equation here. Delta P equals our average force times our change in time. So if this increases as it does for car B, that average force decreases.